So welcome to UV Physics Academy. So here we are discussing the solutions of quantum computation. So the next question is about anti-commutation relation of Pauli matrices. If I is not equal to j, we have to show that this anti-commutation relation equal to 0. Okay, so first let me define what is this anti-commutation relation. Whenever A and B are two operators, the anti-commutator is defined as AB plus BA. Right. So now in the earlier classes we have already defined the product of this Pauli matrices sigma I into sigma j equal to, this is a Kronecker delta ij identity plus iota epsilon ijk sigma k. Now let us take the reverse order. Sigma j sigma I, this is equal to the same, just take the same order, delta Kronecker delta ji identity plus iota. So this is the Levi-Civita symbol. Take in this order only, that is a j I, third index is a k, and this is a sigma k. And in the earlier classes I have already discussed the properties of this Kronecker delta and this Levi-Civita. So we know delta ij equal to delta ji as well as epsilon ijk. This is a order even permutation, and if it is the reverse order, this is just minus jik. If you have this reverse order, then you will get minus. Okay, so that means this is equal to minus of epsilon ijk. So if I add these two, now just add, this is a sigma I sigma j. Okay, so just add plus sigma j sigma I equal to, so these two gets cancelled because of this minus, and here we left with 2 delta ij I. So finally here we got this is the anti-commutation relation, sigma I comma sigma j anti-commutator equal to, so we got a 2 Kronecker delta ij identity. So you know the property of Kronecker delta. So here, so if I equal to j, so this is equal to 1, then we will get a 2i. Simple. If I is equal to j, that means what? Sigma I square plus sigma I square. What is the sigma I square? Identity. Plus sigma I square, identity. So I plus I, 2i. If I is not equal to j, then this Kronecker delta equal to 0. That's why this anti-commutation value equal to 0. Right? Now this is our next question. So here we have to verify this, the product of two operators AB equal to commutator plus its corresponding anti-commutator by 2. Okay, so if you have this commutator definition, let us say A and B are two operators, A cap comma B cap commutator is defined as AB minus BA. Similarly, this anti-commutation relation A comma B anti-commutator equal to, this is AB plus BA. Now just add these two. So once you add, these two gets cancelled. So we got here 2AB. Okay, and this is nothing but the sum of these two, A comma B commutator plus A comma B anti-commutator. So from this we can write, the product of AB, equal to 1 by 2 into commutator A comma B plus anti-commutator A comma B. That's it. So whenever we have the product of two operators, we can write it as a linear combination of commutator and its corresponding anti-commutator by 2. So by using this relation, here is our next question. So they are asking to show that this product. Okay, so right. So here we have Pauli spin matrices sigma j, sigma k. So one thing we have already in the 2.40 problem, I think earlier video. So if you see the commutator value, that means sigma j comma sigma k commutator. I think it is a 2.40 problem. Please see the earlier problems, please. So there we have already derived. This is nothing but 2 iota epsilon ijk. Oh, sorry, here jk taken. It's okay, no problem. So this is iota. So that's why jkl sigma l. And just recently, in the earlier problem, yeah, first here, the anti-commutation relation is nothing but 2 Kronecker delta I. Okay. So commutator contains Levi-Civita and anti-commutator contains Kronecker delta. So sigma j comma sigma k anti-commutator equal to, this is a 2 delta not ij, this is a jk I. That's it. So just earlier problem we have already shown that the product of two operators A, B, it can be written as the linear combination commutator and plus the corresponding anti-commutator by 2. So by using this, I am taking the product of sigma j, sigma k, because he is asking this product sigma j and sigma k. So by using this relation, I can write 1 by 2 the commutator sigma j comma sigma k plus anti-commutator sigma j comma sigma k. So now if I substitute these values, these two and these two, and here these two also gets cancelled, then what's the remaining? Iota epsilon jkl sigma l. Okay, plus that 2 gets cancelled, that is delta jk into I. Okay, so now if you just rewrite like this, this is nothing but sigma j sigma k equal to delta jk identity plus iota, this is a sigma jkl into sigma l. So if you use the summation rule, Einstein summation rule, so in the tensor notation, so here we have index L is repeated twice, that's why this is the summation over L. That's it. So if you have any doubt, so please contact. And the next they are asking if these two operators A comma B satisfies these two relations, that means the commutator is a 0, anti-commutator is also 0. Then they are asking A is invertible and show that B must be 0. If A is invertible, B must be 0. Okay, fine. So A comma B, here they have given commutator A comma B equal to 0 as usual, anti-commutator A comma B equal to 0. Again we will use this same relation, earlier we have derived this. So the product AB equal to the linear combination 1 by 2 A comma B commutator plus A comma B anti-commutator. So already this is a 0 and this is also 0. So we can say AB equal to 0. Now let us multiply on both sides with the A inverse. Then it is A inverse A B equal to 0. So this A inverse A equal to I, that implies B equal to 0. So if A is invertible, then B must be 0. Okay. Right. So our next question, this one, AB a commutator A comma B whole dagger equal to B dagger comma A dagger. So this is also easy. Now here we have the commutator A comma B definition. The commutator is defined as AB minus BA. Now let us apply the dagger, that means a Hermitian conjugate. Let us apply Hermitian conjugate. Then this is nothing but AB minus BA whole dagger. So this is nothing but AB whole dagger minus BA whole dagger. So we can write this as AB whole dagger equal to B dagger A dagger minus BA whole dagger equal to A dagger B dagger. So again this is in the form of commutator. So this can be written as B dagger comma A dagger commutator. So finally we got A comma B commutator whole dagger equal to B dagger comma A dagger, right? And this is our next question. They are asking to show that A comma B commutator equal to minus of B comma A. That means antisymmetric relation. So this is nothing but antisymmetric. So every commutator is antisymmetric. Okay. So this is also easy. Now for example, if you take A comma B commutator definition, which is equal to AB minus BA. Now let us take minus common. Then it is BA minus AB. So we can write this as a commutator form, that is a commutator B comma A. So always every commutator satisfies antisymmetric property, that is A comma B equal to minus of B comma A. If you interchange the positions of these two operators, always you will get a minus sign. Okay, right. Next question. So here they are asking, if A and B are a Hermitian, show that iota A comma B commutator is a Hermitian. Actually, commutator is anti-Hermitian. Iota A comma B commutator is Hermitian. Okay, let us discuss both. Now here they have given operator A and B are Hermitian. So what is the meaning of a Hermitian? So Hermitian operators means A dagger equal to A as well as a B dagger equal to B. Okay. Now, so I'm taking the commutator A comma B whole dagger. So earlier already we have shown that A comma B whole dagger equal to B dagger comma A dagger commutator. So by using that, I can write this as a B dagger comma A dagger. But you know, A and B are Hermitian, so that's why we can write this as B dagger is nothing but B and A dagger is nothing but A. That's it. So again we can write this as a B comma A, earlier property, A comma B equal to minus of B comma A. So this is nothing but minus of A comma B by using antisymmetric property. So finally we got A comma B commutator whole dagger equal to minus of A comma B. So something dagger equal to minus of that is nothing but anti-Hermitian. So this is the property of anti-Hermitian. So commutator satisfies anti-symmetric property, commutator satisfies anti-Hermitian property. And let us go to the question. So here they are asking to show that iota A comma B, whether it is a Hermitian or not. That's why I am applying a dagger to this. So once you apply the dagger, iota dagger is minus iota A comma B commutator whole dagger. We know A comma B whole dagger equal to, this is minus iota as usual. This is nothing but B dagger comma A dagger. Just use the property, nothing. It's very easy. Now here this is a minus iota, b dagger is nothing but b, a dagger is nothing but a, because a and b are Hermitian operators. Now again I am using the antisymmetric property. This b comma a equal to minus of a comma b. So minus minus plus iota a comma b. So b comma a is nothing but minus of a comma b. So this is minus minus plus. So finally iota commutator a comma b whole dagger equal to iota a comma b. So something dagger equal to, again the same, that is a Hermitian or a self-adjoint. That's it. If you have any doubt, so please contact. Right. So here onwards, earlier questions are a bit easy only. Now here onwards it is about a polar decomposition. So left polar decomposition, right polar decomposition. So in this problem we are not discussing both left and right, any one thing we can take. And here they are asking a polar decomposition of a positive matrix and unitary matrix and Hermitian matrix. Okay, first let me explain what is this polar decomposition. So polar decomposition. So for example, there is a matrix A, operator A. So this, according to this polar decomposition definition, A can be written as something J into U, where U is a unitary matrix. We will find what is that unitary matrix. Okay, and what about this J? This J is given by J equal to, this is under root A dagger into A. Okay, so this is the basic definition, and now once you got this J, again you will find U equal to, this U equal to, bring this J this side, that means J inverse into A. That's it. So once you got this J and U, you will take it and multiply here, either left side or right side, like this. So then it is a polar decomposition. But remember, this process is easy only when this operator or matrix A is diagonalizable. If it is not diagonalizable, it is a little bit lengthy. That is the next, I think, 50th problem. Okay, so now let us come back to the question. Let us take the first one. So the first one is a positive matrix. Positive matrix. Okay, now I am taking this positive matrix as just P. So P equal to some J into U, where U is the unitary. We have to find that. And according to the definition of a J, what is a J? J equal to under root this P dagger into P. So since it is a positive matrix, it's a Hermitian. So we can write this as under root P square. So then J equal to how much? P. Okay. So now, because it is a diagonalizable, and one more thing, it is a diagonalizable. Okay. Now, once you got this J, you will take it and substitute. And after that, we have to find U. So U equal to, just bring this J this side, J inverse into P. Already we know what is a J. P. J inverse is nothing but P inverse into P, which is nothing but I. So in this problem, our U is nothing but identity. So the polar decomposition of that positive matrix can be written as J. Already we got that P, and this U is nothing but I. That's it. And let us take the second one, still not understanding. And here they are asking about unitary matrix. Okay. So now I am taking unitary matrix, which is equal to J into some another unitary matrix. Let us take V. Okay. Remember, this must be unitary also. Now from the definition of this J, let us find J equal to whatever the matrix you have under root U dagger into U, which is nothing but I. In this case, our J is nothing but I. Next I want to find this v. V equal to, so bring this j this side, j inverse into u, or you can multiply j inverse like this also. Okay, it's okay. What is the j here? You got I, j inverse again I, so which is equal to iu, which is again u. So in this case our v is nothing but u, and our j is nothing but I. So we can write u equal to j I, that v is nothing but u, of course, u equal to iu. And the third one I will explain here. Third one is about Hermitian matrix. So Hermitian matrix. Okay, so how to write this polar decomposition of Hermitian matrix? So what is a Hermitian matrix? H dagger equal to H. Let us. Now I am taking this matrix H equal to polar decomposition form J into U, where U is unitary. We have to find that. And first, what is the definition of a J? J equal to under root H dagger into H. Okay. So H dagger is Hermitian. So that's why we can write J equal to under root H square. Now shall I cancel this root and square here, and shall I write H? I repeat. As per the mathematics, shall I cancel this square and root, and shall I write this as H? The answer is no, because this is not equal to H. The reason is H square is not H. Okay, H square equal to I. So I hope everybody know what is H square. H square equal to I. So under root I, again it is I. So in this case, our J is not equal to H. Be careful. Our J is not equal to H. Our J equal to I. So that implies our J equal to I. Now take it and substitute. And now I am going to find U. So U equal to J inverse H. And J is nothing but I. So that's why this is nothing but IH. So which is again H. So as per this spectral decomposition, we can write our H is equal to, in the place of J, I, in the place of U, it is H. So H is equal to I, H. That's obvious. So H is equal to I, H. That's it. Right. Okay. So if you have any doubt, so please contact. And the next question. So this is asking to express the polar decomposition in the form of outer product representation. Okay. So let us take this is the matrix. Which matrix? Some normal matrix. That means which is diagonalizable. Diagonalizable. Okay. Let us suppose the polar decomposition representation A equal to some J into U. So where U is unitary, okay, and this J, how to get this J? J equal to under root A dagger and A. Our matrix is a normal matrix, a Hermitian, so we can write this as under root A square, which is equal to A. So your J is nothing but A. And here we have to represent in the outer product form. So that's why I have to take the spectral decomposition matrix representation. Spectral decomposition of the representation of a matrix. If A is a matrix, we can represent it as the outer product form, summation over I, lambda I, psi I, outer product, where psi is the eigenvector and lambda is the eigenvalue. So here let us suppose it is, we don't know the order. So if it is a 2, we can write it as a lambda 1 outer product psi 1 plus lambda 2 outer product psi 2. Okay. Right. So here we got the J. So J is nothing but what? Summation over I, lambda I, psi I, because J is nothing but A. Next we have to find u. Okay, so earlier I already discussed u is nothing but just bring this j this side, so j inverse into a. So already j inverse is there. Okay, so we can get, I mean, we will get this product of these two matrices, and finally we'll get in this form only. Let us say summation over I, some other eigenvalues. That means we have to find the eigenvalues of this, and we can find the outer product form. Let us say summation over I mu I, sorry, j I will take, because already index I have taken. This is a psi j. That's it. So some other outer product representation, because this is the u is nothing but a product of these two matrices. Okay, so once you got both, and final representation of your matrix is nothing but ju. Left and right, the difference is you will write u this side, otherwise u here. That's it. That is the only difference between that left and right. Okay, so here j already there, summation, and u is also there. So we can write summation over I j lambda I mu j. You can write the constant outside, and after that what we have psi I outer product, and this one u, which is again outer product psi j. That's it. So this is the polar decomposition in the form of outer products. Just we have to find the outer product form of j first, and after that u is nothing but j inverse a. You will get another matrix. So again you have to find the outer product form. You just multiply both. That's it. And the next question, this is a little bit lengthy and little bit more algebra is there, because the problem is this matrix is not diagonalizable. So I will take this problem separately in a separate video. The meanwhile, I request you, earlier I already discussed why this is not diagonalizable, because why it is not diagonalizable means here we have to find its arithmetic mean, and here a geometrical mean. So arithmetic mean is nothing but lambda minus 1 whole square equal to 0 here. This is the characteristic equation. So here the arithmetic mean equal to 2. And geometrical mean is nothing but rank of A minus lambda I matrix. If you take it and lambda is 1, if you take it and substitute, you will get the rank is nothing but a geometrical multiplicity, which is equal to 1. If these two are not equal, that means arithmetic multiplicity is not equal to geometric multiplicity, then it is not diagonalizable. Not diagonalizable. So this actual problem I will discuss separately. Okay, so if you have any doubt, so please contact. Thank you.